All right, welcome to part 8 of Learning Rust series. This is Rune Connor. So today we are going to be looking at references and borrowing. Okay, so it's talking about the tuple code in listing 4-5. Let's try and go there. 4-5, if we can find it. It's 4-1, 3, 5. All right, so it's talking about this code. Let me just paste it in so that we know what it's talking about. Tuple code in 4-5 is that we have to return the string to the calling function. So return the string, this s, to the calling function. Calculate length right there to the call here. So we can still use the string after the call to calculate length, because the string was moved into calculate length, right? It was moved, meaning at this point, if you don't return it from the function, you're not going to get this s2 again inside your code to show it, right? And let me get a PowerShell going there. Yep. Let me go to my directory here, projects, objects, and then I was doing ownership, I think. Let me see, ownership, cd ownership, and then cargo run. The length of hello is 5, right? So we can have s2 here only if we get it from the function as a return right here. If we didn't get it here, the s2, then we would not have access to it. Do we have access to s1, for instance, after the function call? We do not, right? We've seen this in the last part, right? It says, where's our value borrowed here after move, right? S1 was moved into the function. So after the function call, we no longer have access to S1. That's the problem with, like programmers have with Rust. They're coming from C family languages. Okay, so instead of doing that, we can provide a reference to the string. A reference is like a pointer in that it's an address we can follow to access the data stored at that address. Okay. That data is owned by some other variable. So you don't transfer ownership, you just reference the data. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type for the life of that reference. Here is how you would define and use a calculate length function that has a reference to an object as a parameter instead of taking ownership. Okay, let's paste that. Here we have calculate length, and it takes a string reference, which is denoted by this ampersand, I believe, and then returns a usize type, which is the length of the string. First, notice that all the tuple code in the variable declaration and function return value is gone. Let's see. So it used to be like this, right? Okay, so the tuple is gone. These tuples are gone. The variable declaration there, is that it? The function return value is gone. Second, note that we pass ampersand s1 into calculate length, and in its definition we take the ampersand string rather than string. So when we are calling the function here, calculate length, we are passing to the function the reference of this string object that is pointed to by S1, I guess. These ampersands represent references, and they allow you to refer to some value without taking ownership of it. Figure 4-5 depicts this concept. Okay. S is something. What is S? Is there an S here? Okay, so that's S, which is the parameter of this function. And once you pass this argument to the function, the S starts, the pointer of S, I guess, starts pointing to the pointer of S1, which is pointing to the 0 index of this string object. So S1, this is basically the pointer of S1, or the reference rather, S1. And that's what we're passing to the function. So we're passing this PTR value to the function, and therefore the function's parameter starts pointing to that pointer, which is pointing to the object. Interesting. The opposite of referencing by using ampersand is dereferencing, which is accomplished with a dereference operator, which is an asterisk. We'll see some uses of the dereference operator in Chapter 8 and discuss details of dereferencing in Chapter 15. Okay, let's take a closer look at the function call here. Let's get that code here. Let S1 string from hello. Okay, so you're creating a string from the string literal hello here. And then let len calculate length S1. Let len usize. Okay, so this portion is added by the IDE itself. It's not actually here in the actual code. Okay, let len calculate length ampersand S1, or reference S1. The reference S1 syntax lets us create a reference that refers to the value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference stops being used. Okay, yeah. Likewise, the signature of the function uses ampersand to indicate that the type of the parameter S is a reference right here. Let's add some explanatory annotations. S is a reference to a string. Here, S goes out of scope, but because it does not have ownership of what it refers to, it is not dropped. What do you mean? I think S should be dropped, but not the object that it's pointing to. Anyway, the scope in which the variable S is valid is the same as any function parameter scope. Right. But the value pointed to by the reference is not dropped. Right, yes. So it does not have ownership of what it refers to. What it refers to is not dropped. Right. Okay. Because S doesn't have ownership. When functions have references as parameters instead of the actual values, we won't need to return the values in order to give back ownership because we never had ownership. Right. So if you want to not deal with the ownership stuff, you need to pass by reference to functions. We call the action of creating a reference borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back. You don't own it. So what happens if we try to modify something we're borrowing? Try the code in listing 4-6. Spoiler alert, it doesn't work. Yeah, figured as much. So I'm just going to type this to practice typing Rust. Main, and then let s be a string created from the string literal hello. And then we're going to call a change function with reference to s. Function change definition is some string, which is a reference to the string type. Some string dot push string. Push adds to the end of the string hello world. Okay. And it's not going to work. The linter is telling me cannot borrow some string as mutable as it is behind a reference. Some string is an ampersand reference, so the data it refers to cannot be borrowed as mutable. Consider changing this to be a mutable reference. Okay, let's try to run it. Cargo run. Okay, I don't want to do that actually. Change the... Let me just do this. Okay. Cannot borrow some string is mutable as it is behind a reference. Yeah. Help. Consider changing this to be a mutable reference. If you do ampersand mute, that's going to do it. But I don't think I want to do that. Just as variables are immutable by default, so are references. We're not allowed to modify something we have reference to. We have a reference to, right? Mutable references. We can fix the code from listing 4-6 to allow us to modify a borrowed value with just a few small tweaks that use instead a mutable reference. So here, let mute s. Let mute s is a mutable string now. And then this is going to be mute s, right? And this is going to be a mutable string. Cargo run. Let's do it again. We're not printing anything, I guess. We didn't get any errors, so. First we change s to be mute, then we create a mutable reference with the ampersand mute s, where we call the change function and update the function signature to accept the mutable reference with some string mute string. This makes it very clear that the change function will mutate the value it borrows. Mutable references have one big restriction. If you have a mutable reference to a value, you can have no other references to that value. If you have a mutable reference to a value, you can have no other references to that value. Interesting. This code that attempts to create two mutable references to s will fail. Right. And the error is cannot borrow s as mutable more than once at a time. This error says that this code is invalid because we cannot borrow s as mutable more than once at a time. The first mutable borrow is in R1 and must last until it's used in the print line macro. But between the creation of that mutable reference and its usage, we tried to create another mutable reference in R2 that borrows the same data as R1. Right, so here So this is not possible. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. Control is key in Rust. It's something that new Rustaceans struggle with because most languages let you mutate whenever you'd like. The benefit of having this restriction is that Rust can prevent data races at compile time. So it's about concurrency. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data. There is no mechanism being used to synchronize access to the data. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem by refusing to compile code with data races. Yep. As always, we can use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. So R1 goes out of scope here, so we can make a new reference with no problems. Right, so this, you can have mutable references to something, multiple of them, provided they're in different scopes, of course. But I wonder if you could do this. Probably not. So let's say we have this before R1. Can you do that? Yep. You just get unused variable. Warnings. Ownership generated 2 warnings. If this is intentional, prefix it with an underscore. Unused variable, unused variable. Okay. All right, so you can do this as well. So this R2 is still in scope down here, but they're just shadowing. Is it? It's not shadowing, it's just... So R2 is valid in this scope, R1 is valid in that scope, I guess. Okay. Rust enforces a similar rule for combining mutable and immutable references. This code results in an error. No problem. R2, really? Oh. Okay, immutable. These are immutable references. So this is a mutable object string. This is an immutable reference to the string. This is another immutable reference to the string. But then this is a mutable reference to the string. Here is the error. Cannot borrow S as mutable because it is also borrowed as immutable. We also cannot have a mutable reference while we have an immutable one to the same value. Users of an immutable reference don't expect the value to suddenly change out from under them. Right. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of the data. Multiple immutable references are allowed. So immutable references are basically read-only, right? They're used for reading data. They're not used for writing data. Because no one who is just reading the data has the ability to affect anyone else's reading of that data. Okay. Note that a reference's scope starts from where it is introduced and continues through the last time that reference is used. For instance, this code will compile because the last usage of the immutable references, the print line occurs before the mutable reference is introduced. Variables R1 and R2 will not be used after this point. The last use of immutable references occurs before the mutable reference is introduced. Interesting. So here, immutable borrow later used here. Immutable borrow occurs here, immutable borrow occurs here, immutable borrow later used here. Okay, this is now going over my head. For immutable reference, R3 is created. These scopes don't overlap, so this code is allowed. The compiler can tell that the reference is no longer being used at a point before the end of the scope. Okay, I see. If you don't use it again, it's fine. But if you try and use it again, it's not fine. Let's try this. Okay, so if I try this line again after this print line to R3, this is gonna give me an error. If you try and use it again, if you don't have this line to use your immutable references, then okay, then the code runs without a problem. So the compiler determines scope based on use as well, right? Not just these brackets, but last used. So if the R1 and R2 are last used here, they reach their end of life and are discarded. Interesting. These codes don't overlap, so this code is allowed. The compiler can tell that the reference is no longer being used at a point before the end of the scope. Even though borrowing errors may be frustrating at times, remember that it's the Rust compiler pointing out a potential bug early at compile time rather than at runtime and showing you exactly where the problem is. And you don't have to track down why your data isn't what you thought it was. Dangling references. In languages with pointers, it's easy to erroneously create a dangling pointer, a pointer that references a location memory that may have been given to someone else, by freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. Let's try to create a dangling reference to see how Rust prevents them with a compile time error. Okay, let's do this. Function dangle, no parameters, returns a reference to a string type. Let s string from hello, and then returning this reference to s, I guess. Let reference to nothing, string dangle. Try and run it. Error, could not compile ownership due to previous error. What is it? Missing lifetime specifier. Expected named lifetime parameter. This error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in chapter 10. But if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. there is no value for it to be borrowed from. Let's take a closer look at exactly what's happening at each stage of our Dangle code. Dangle string. Dangle returns a reference to a string. Okay. S is a new string, right? And we return reference to the string S. Here, S goes out of scope and is dropped. Its memory goes away. Danger, right? So this object in memory is no longer valid after this point. It's freed. If you return a reference to the freed object, that's dangerous. Because S is created inside Dangle, when the code of Dangle is finished, S will be deallocated. But we try to return reference to it. That means this reference would be pointing to an invalid string. That's no good. Rust won't let us do this. The solution here is to return the string directly, right? Not the reference. This works without any problems. Ownership is moved out and nothing is deallocated. Okay. The rules of references. Let's recap. At any given time, you can have either one mutable reference or any number of immutable references, right? References must always be valid. All right, the slice type. We are going to talk about this in the next part of Learning Rust series.